All right, assignment 5.5. Let's go. As always, you should try it first. That's how you learn. So this assignment's connected to exponentials or logarithms. Logarithms and exponentials. All right. So when I see a fraction, one of the things I look at is take the derivative of the denominator. Is it like terms to the numerator? Then it's a logarithm. That's simple. So I look at the denominator. The derivative of the denominator is 1. That's the hook it should be. What was it before? Over what it became. That's 2. And now you're done. So this is ln. Don't forget the candy bars, but there's no candy here at the end. And then, because it's a definite integral, we have one more step to do. Now, some properties we have to know that will help us on multiple choice. Ln e is equal to 1, and ln 1 is equal to 0. Those are like really helpful ones to know that show up all the time to simplify it. So if that's true, this answer is just 2. This I should know. You can do it. Remember, ln e equals 1, and ln 1 equals 0. Number 2. Again, what do I look at when I see a fraction? What's the derivative of the denominator? That's where the hook comes from. That's the right hook. Now, what was it before? Over what it became. So 4 divided by 2. So then I can start. Oops, this is a logarithm with the absolute value bars. And again, I'm integrating from 1 to 3. So first plug in 3. That gives you 5. 2 again. Plug in 1, and 2 take away 1 is 1. Remember what I said about that one? So ln 1 is 0, so it's really just 2 ln 5. If they really wanted to be fun with you, they could use this and put it as an exponent, and that could be 5 squared, and you could also see the answer is ln 25. Number 3. We're integrating from -1 to 1, 4 to the exponent x plus 1. So here we're integrating an exponential. Where does the hook come from? So the derivative of x plus 1 is 1. We already have that. So we can just integrate with the rule. So the rule is copy it, and then we divide by ln of whatever that base is, which is 4. And then I plug in. So if I plug in 1, 1 plus 1, that's 16, 4 squared. Subtract, plug in -1, plus 1 is 0, so 4 to the 0 is 1. So with common denominators, the answer is 13 over ln 4. Number 4. So what's the rule? So the hook comes from the exponent. We need to know where the hook comes from. The derivative of -2x is -2. And then what was it before and what did it become? And now the rule. And the rule for you is to copy it. So the hook is unhooked and then copy. And then I'm going to plug in 2. And then I'm going to plug in 0. And e to the 0 is 1. So an answer here would be -1/2 e to the -4. A negative times a negative plus a half. What are different ways you could possibly see this? We have a common denominator of 2. E to the 4th would also... Oh. I'm just going to leave it as that. You could get common denominators. Know that e to the -4th is actually in the denominator. You could multiply top and bottom by e to the 4th, get common denominators, write it as one fraction. I'm going to let it go. Number 5. Integrate e, x squared take away 1, x dx. Again, where does the hook come from? The derivative of x squared minus 1 is 2x And what was it before, and what did it become? We need a 1/2. Then you can unhook this. It starts with 1/2. The rule for E is copy it. And this one just needs a C at the end. 6. When I see a fraction, I cycle through possibilities. So one of the possibilities is it's a logarithm. What's the derivative of the denominator? 2x. So what it was over what it became. Next, do the logarithm of the denominator. And don't forget the candy bars. The candy bars when you do a logarithm. Number 7. What's the derivative of the denominator? It does not match. This is not a logarithm. It's a monomial. So I'm going to write it as two fractions. X squared over x is x, and negative 1 over x as calculus friendly. So instead of 1 over x, I write it as x to the negative 1. And now we just integrate with the power rule, which is add 1 to the exponent and divide. Add 1 to the exponent. So 1 over x is a logarithm. So what happened there, to make me notice that, is that when I add 1 to the exponent, I get 0 divided by 0. So what does that mean? So now when I go back and think, okay, that's really just 1 over x, so what's the antiderivative of 1 over x? And that's where the logarithm comes in, to think through. Number 8. What's the derivative of the denominator? That's 2y subtract 3. If you don't see what the number is, what it was before, and so on, factor out at 2 so that you can see it better. So if you factor out at 2 here, you can see the difference between what it was and what it became is 2 over 1. And then it's the logarithm of the denominator. And then plus c. Number 9. The derivative of the denominator is not like terms of the numerator. So instead, what we have to do here, when the power terms are the same, is we have to divide. So we need to do long division. It's okay. X goes into x once. You just divide the power terms and then find the remainder. Be careful when you subtract a negative. And so this is really just 1 plus 2 over x minus 1. It's okay. Then the antiderivative of 1 is x. The antiderivative here of x is a logarithm. Now the derivative of this would be 1. Let me just show you here. So if I separate this, then maybe you can see it better. So the hook comes from the denominator. So the derivative of x minus 1 is 1. What it was before over what it became. There it is. And then don't forget the bars and the candy. Number 10. All right, so the derivative of this is not going to match this. So I'm going to write it calculus friendly. The hook, the derivative of the base is 1. And then what it was, negative 1 over 1. So this is going to be negative in front. And this is the power rule. So we're going to add 1 to the exponent and divide by that exponent. Plus c. Number 11. So I'm going to write it calculus friendly so I can see it a little bit better. Oops. It's not a logarithm because it's a cube root, and the derivative of that is not going to match on top. See, the derivative of the denominator then would be like 1/3 this to the 2/3. Like, it's not going to match. So I need to write it calculus friendly to see where the hook comes from. So that's u squared plus 1. This is 1/3, so it's negative 1/3. And now I can see where the hook comes from. So the derivative of the base is 2u. What it was over what it became, then unhook, and then we add 1 to the exponent, and then the reciprocal, and then don't forget that. That is 9/4. It's fine. Number 12. All right, I'm going to rewrite this. So I'm going to show you what I see. I need to see connections here to be able to understand how to do the antiderivative. I know the derivative of ln x is 1/x. So because I see that relationship, I'm going to write it like this. So can you see? As soon as you see it, I see 1/x, and the square root of ln x is here written calculus friendly. The hook comes from the base, and it matches. So then all I have to do is add 1 to the exponent, and then the reciprocal. Done. Number 13. All right, so what kind of things do I see again? So I know the derivative of this is 1/x. So let's just rewrite this. So this 2, I'm going to write in front, and then I have 1/x, and then I have 1 plus ln x to the -5. So I rearrange it algebraically. So the 2 can be written in front. I have 1/x, which then matches the derivative of the base, -5. So it's all calculus friendly, ready to go. I can unhook this, and then I add 1 to the exponent and divide by that exponent. And you could write that as -1/2. Number 14. The derivative of the denominator, the derivative of sine y is cosine y. And then the derivative of -2 is 0. So I don't even know why I'm rewriting. This is perfect. So the derivative of the denominator matches the numerator. This is a logarithm. Plus c. Don't forget the candy bars. Number 15. So what kind of things do I see here that could be helpful? So I see there's a relationship here. So cotangent squared x divided by cotangent x is just cotangent x. And then 1 over cotangent is tangent. So I have to see that trig connection with identities. So again, squared here just leaves me with 1 cotangent. 1 over cotangent's tangent. These are rules that we learned. So they are logarithms. Sometimes, let's say I forget. So I know that cotangent or tangent. Let's start with tangent. So I know tangent is sine over cosine. And the derivative of cosine is negative sine. So I know this one's negative. Well, the other direction, if it's cosine over sine, the derivative of sine is cosine. So that one's positive. So this one's positive, and it's sine. This one's negative. Now a negative and a negative will make it positive. Remember, and it's the derivative of the denominator. So it's the denominator that goes inside a logarithm. Number 16. I know that math always reminds you that you haven't got there yet. Math reminds you there's always more to remember, more to practice, more to figure out. That's good. You're never there. You're always trying to get closer to there. That's it. I'm not there. I'm trying to get closer to there. All right. Tangent squared. Let me look. Oh, yeah. So this is a Pythagorean identity. Sine squared plus cosine squared equals 1. And if you change it, I'm just going to tell you. It's secant squared minus 1. The derivative of 3x is 3. So I need a 1/3. And just, oops, don't forget the dx's. I'm separating it into 2. So I can unhook. The antiderivative rule for secant squared is tangent. And the antiderivative rule for 1 is just x. Done. Number 17. Yeah, so I thought. So the derivative here doesn't match here. Writing it calculus friendly is going to help. I'm going to have to do a u substitution. So u is going to equal the square root of x. Which means x is u squared, which means the derivative is 2u du. Come back here. So I have 2 plus u, and instead of dx, I put in 2 du. There it is, just like that. So I take out the root x and put in u. I take out dx and put in 2 du. These are going to be multiplying. And then let me put them together and then think, what am I going to do? And so right away I noticed the derivative of the denominator is 1. So I can just put the 8 in front. And then the last step after you do that is to then plug in what u is. Oh, you know what I forgot? It's a u. I forgot the u. That's important. So this is 8u. So at this step, my brain didn't want to do this. So we have this u substitution. At this point where we have power terms that are the same, we have to do long division. I'm sorry. We'll do it together. So that's 8. That's 8u and 16. That gives me negative 16. So integrate. We have 8. We have negative 16. Now we can do the antiderivative, and then you got to plug back in. So the antiderivative of 8 is 8u. The antiderivative, the derivative here is 1, so 16 will be in front, and then ln 2 plus u plus c, and then put u back in. So u is the square root of x. Man, it looks simple, right? That's something you have to do u substitution, long division, all of that for something so sweet at the beginning. Number 18. We did it together. All right. Differentiate. So what's the derivative here? Oh, let's write this as 2/3. And then we can do it. So it's 2/3, then a fraction. The derivative of x minus 1 is 1. Don't put plus c. There's your answer. Number 19. I I look to see if I can simplify first. I can't. So this is going to be the quotient rule. I know some want to write this as a product, then you could do the product rule, but you need to know it. So the bottom times the derivative of the top minus the top times the derivative of the bottom, and then the bottom squared. Number 20. Remember, the derivative rule with absolute value for logarithm is the same derivative rule if it wasn't that way. So if you see absolute value bar, same rule. So I'm going to do that goes in the denominator, and then the derivative of this goes in the numerator. So the derivative of 1 is 0, of this is negative 1 over y, and it's done. And if you wanted to, you could write this as negative 1, and the y could go in the denominator like that. Not necessary. 21. So when we have a situation of a variable to a variable, we're going to do the natural logarithm to both sides. That means a property I can use here. And now I'm going to take the derivative implicitly. So this is 1 over y, but there's a y prime. This is going to be the product rule. So the first times the derivative of the second plus the second times the derivative of the first. And then multiply both sides by y. There you go. And if you want not to have y in your answer, like if it's all x's, y equals this, so then you could do a substitution at the end, and then you don't have any y's at all involved. (22) So the derivative of a logarithm is a fraction. What I see is in the denominator. I'm going to write it like this so you can see it. And then the derivative of this is up here. Now, this one has a hook. So do the power rule, and then the derivative of sine is cosine. And that too could be in the middle, or you can use parentheses. That's number 22. I'm always checking to make sure that we did it correctly. 23. We could also simplify this, by the way, at the end, like sine squared over sine cubed. Like there's ways to simplify it. I could show you that too. So sine squared over that is 1 over sine, which is cosecant. And then cosine over sine, I already took, and that leaves me just with cosine. Is that right? Oh, well, try it again. So this makes this just a sine. That's better. And then cosine over sine is cotangent. But this is good. That's not necessarily better unless it's multiple choice. 23. All right, take the derivative. That's 2x. I'm going to write this as ln y squared. I guess you can do 2 ln, same thing, right? So that's 2, and then, so it's 2. The derivative of ln is 1 over y, but it needs a y prime, because the derivative of y is y prime. The derivative of y is y prime. I'm going to subtract it. I'm going to subtract it. I'm going to factor out a y prime and then divide. I'm not trying to be like super awesome about it. It's fine that it looks like that. Number 24. This is the domain and range without using a calculator. Okay. So a logarithm cannot be 0 or negative. So what is the 0 of this? So it must be not greater than or equal to. It must be greater than 0, or you can say from 0 to infinity. For number 25, because you are squaring it, the only answer that x can't be is 2. So positive 2 would give you 0. Everything else would be positive. 26. Or was that A and B? Sorry. This is A and this is B. Oh, did it say the range? So the range is going to be all real numbers. For both. A logarithm goes up forever and down forever. There's no restrictions for the range. 25. It's going to be a good one. We really need to, these are the ones that give you a better grade on the exam, right? That you can do this. All right, use a calculator to find each of them. So that's nice. So we still need to set this up. So average value is integrate. And I'm going to integrate from 1 to 4. And once g at x is defined, you can just put g at x in and then divide by the difference of the bounds. If you use your calculator, I'm going to let you do that. It is, or is it average rate of change? Boo. I found average value. That's B. Sorry. And so for part B, if you use your calculator, it'd be this. For A, what would it be for A rock? That's y2 minus y1 and so on. So in this case, from 1 to 4, it would be g at 4 subtract g at 1. That's the setup. Use your calculator. And if you did it correct, you'd get 0.003. You should try until you get it right. Part C, IROC is just the derivative. This is going to be the quotient rule. So the bottom times the derivative of the top, which is a product rule. So the first times the derivative of the second plus the second times the derivative of the first, which is 1. Subtract the top times the derivative of the bottom, and then the bottom squared. Oh, and it said, sorry, find it at 1. So use your calculator and find the derivative at 1. So you press menu, calculus, derivative at a point, and put it in at 1. And if you did it correctly, you would have got the answer. But how fun that I did an extra step for you. Could you take this derivative without a calculator and find it? So there's your answer. If you round it, it's 0.368. All right, D. Find the x values horizontal tangent. So horizontal tangent means when the derivative is equal to 0, because a horizontal line has a slope of 0. That's what derivative means. So you would go menu, algebra, solve. So first you go solve, then you go menu, calculus, and do the derivative of g at x equal to 0, comma x, solve it. So where's the derivative equal to 0? Solve it. See if you can do it. It's 0.259. And another answer is 2.239 or 40. So see, try it. Set it up. Can you get the answer on your own? Be a little independent. 26. Set up one or more integrals which can be used to find the area. Area is an integration question. We have f at x equals x squared. And we have g at x equaling, I'm going to rearrange it, x cubed minus 3x squared plus 3x. So I'm going to try to do a little graph because that's going to be helpful. Maybe helpful. So we have x squared. If I make this equal to 0, well, so definitely 0 is a point that they share. do it this way too. We can make it equal to each other to find the bounds. So I'm going to make it equal to 0 and then go from there. So I subtract x squared, make it equal to 0, factor out an x. This is now factorable compared to the other one that I was looking at. So that's -3 and -1. So we have 0, 1, and 3 is where they intersect. So at 0, at 1, and at 3 that they intersect. So what do I know is it goes down to the right and it goes up to the left, right? So I'm going to use those 3 points to understand this. So there's the area trapped. And so 1 is going to go 0 to 1. Which one's first and which one's second? So top would be g at x, and the bottom's f at x. And then it goes 1 to 3. Now the parabola is on top, and the cube is underneath it. This is, you could use a calculator. We didn't, right? We did that, and then we used the points of intersection, understand the end behavior, where it goes up to the right and down to the left to have a sense of it. 27. Turn the page. All right, we're more than halfway done. We got this. 32 minutes in, all good. Use the alternate form. What? That was like a million years ago. So, I'm going to give you advice. When something like this happens, go to the index, alternate form of a limit definition, and then go to the last page, right? And actually, like, I don't remember it. So, like, what do I do if I don't know the alternate form of that? So I'm looking at alternate form, limit definition of a derivative. And I know it's at the beginning. So I think, okay, is it 1, 2, 1, 3, 1, 4? Which one is it? 1, 5? There's the limit. So I like look, okay, 1, 4 is the limit definition of a derivative. What's the alternate one that they're talking about? Right? And so then I look, okay, there it is. It's the alternate form of a limit definition. What does it look like? Oh, I put a box around it. So it looks just like this when you're approaching C. So I'm going to use this then to remember, right? So for 27, oh, I lost my page. I got it. Okay, so that's just some advice. So I want to know, is that where I'm at? It's not where I'm at. Let's try it again. So I was on the wrong, see, lost my place. Here we are. All right, I want to know the derivative at 3 using limits. So it's the limit as t approaches 3, the function, subtract f at 3. So that's 3 squared times 2. That's 15. And then the bottom is as t approaches 3. Let's hope this works. So factor out at 2. Factor to difference of squares. And then you can remove the discontinuity, right? And once you remove the discontinuity, then you plug 3 in and get your answer. So 3 plus 3 is 6 times 2, and the answer is 12. We can double check. If you take the derivative here, it's 4t. And then when you plug in 3, 4 times 3 is 12, so it totally works. I know, right? What we don't practice, we totally forget. We all forget. It's the ability to go back to remember and caring about it. and putting the work into it. The graph of f at x is shown to the right. And it says, approximate from negative 12 to 12 using trapezoidal approximation with interval widths of 4. All right, that's been a while too, right? So we're going to do it together. So let's see, what are the things I care about? So the width of each trapezoid. Well, we just told the width is 4. So the formula starts with 1/2 and then the width, which is 4. The first height is at negative 12. At negative 12, the height is negative 10. Then we're going to count by 4s. So then negative 8, that height is 0. Negative 4, that height is 20. At 0, the height is 30. At 4, the height is 20. I'm just looking off the graph. At 8, again, the height is 0. And then at 12, the height is negative 10. And notice the first height and the last height I don't double. And then I just plug in what the heights are that I see off the graph. For part B, use a midpoint rectangles of equal width where n equals 3. So because they say n equals 3, so first of all, write down what you're doing. To find the width now, you take the top, subtract the bottom, that's 24, divided by how many rectangles? So each rectangle is going to be a width of 8. So the first rectangle for midpoint goes negative 12 to negative 4. So the width, and so the midpoint would be 0. The next one would go negative 4 to positive 4, so the mid value would be 30. And then the last one goes from 4 to 12, and the mid value would be 0. And that's it. That's 240. Well, that's a good answer there. 29. For number 29, the region R is bounded by y equals e to the x, y equals 1, x equals 1, x equals 3. Without using a calculator, sketch the region. All right, don't be intimidated. Here we go. Can you try that? First, like press pause and try to graph. What does e to the x look like? Think. Do your best. If you can't, I'm going to help. So a starting point here would be if you plug in 0, the answer is 1. Can you go from there? Press pause. What does an exponential look like? Well, it goes up to the right, and then to the left, it gets closer to 0. Y equals 1. It goes through that point I just did. X equals 1. And then x equals 3. Let's put it over here somewhere. So it's this area right here that we're looking at. And so I'm going to integrate, obviously, from 1 to 3. Top, subtract bottom. So that's e to the x, subtract 1. And that will give you the area. Oh, don't integrate it. So do the thing, set up, but don't integrate the following. So I don't need to. So that's A. This is B. C is the volume by revolving. The word revolving means it's going to be a circle or two circles. I'm going to revolve about the x-axis. Well, there's a space there. So it's going to be two circles. So the first radius, the big radius, start from like here to here. So it's e to the x, take away 0. And then the small radius is here to here, which is 1. 1 take away 0. D, the volume by square cross sections. Not revolving, just a square, so it's still 1 to 3. Square just means the base squared. So it's just top subtract bottom, so that's e to the x subtract 1. E, the volume solved by revolving around y equals 1. So if you revolve around y equals 1, there's no space, there's one circle. And again, it's top subtract bottom for the radius. F, volume around X, find the volume, find the volume formed by revolving the region about the line X equals 1. So if I take this around X equals 1, it's going to be a cylinder or a shell, because perpendicular. What's that? It's 2 pi. I need to know what the radius is here. So that's going to be the X coordinate, which is to 1. So the X coordinate subtract 1 is the radius. So let's say you start at 2. What's the radius here for 2? You have to go 2, take away 1 to get the answer of the radius. So it's right, subtract left. So the X coordinate subtract 1. The height of it is top subtract bottom, which is e to the x, take away 1. And that's it. So that's the radius, and that's the height to do the shell method. The perimeter of region R is arc length. So to find that perimeter here around it, so first of all, we have, let's make sure I do this right. So we have 2. This perimeter up here is e to the 1 subtract 1. So here, let me draw it. So like we have like perimeter. So like that's the region we're talking about, right, that I shaded. So this is easy. That's 2. What's this? Take this point, which is e to the 1, take away 1. Take this point, which is e to the 3, take away 1. And the last one's going to be arc length. How do we find arc length again? So it's an integration question from 1 to 3. It's the square root of 1 plus, or to subtract, plus the derivative, right, of e to the x. So this arc length that goes 1 to 3, and there you go. And the derivative of e to the x is e to the x. All right, 30. Oh, you have to square it. Ha. I knew I made a little mistake with the formula. If you forget the formula, do what I did, right? I went right back and looked at it and go, something didn't feel right. So what do you do with this is that it's the derivative squared. There it is. That's a BC topic, so I'm still rusty with my memorization of it. But I'll get there. What number are we at? That was a long one. Number 30. All right. Some algebra work. So it says find A, B, C. So f at 1 equals 10. So right away, I can plug in 1 for x, and I have an equation. Then if I take the derivative, I have another point, -1, 2. So if I plug in -1 for x, there's the other one. So we have -1, 2. We have 1, 10, so we have 2 points here. In fact, I can add this together and eliminate the b. The derivative of that is 2ax plus b. If there's a relative maximum or minimum, then you take the derivative equal to 0, and I would plug in -1 for x. Oh, wait a second. I added. If I actually subtracted here instead of added, I would have eliminated A and C. That's helpful. So I'm going to subtract. That gives me B is equal to 4. I think that's more helpful. So the A's and C's cross out. When you subtract a negative, it's 2B and divide. So now I know what B equals. So because B is 4, then I can plug in 4 for B. Ignore this. So B is 4. And then if I solve this, A is equal to 2. So now I have two values. A is 2, B is 4. And then I'm going to just go back to here and plug in the values I know to solve for C. So C is equal to 4. So you get A is 2, B is 4, C is 4. All right, number 31. F at x equals x minus 1 to the 2/3. MVT does not apply to which interval? So 2/3, when you cube root something, you can cube root any number. So this one is continuous, but 2/3 kind of looks like this. So there's a spot where it's not differentiable. So when x equals 1, it is not differentiable. So the MVT does not apply when it's not continuous and not differentiable. So it's not differentiable at positive 1. So because of that, A, it does not apply. B, it does apply, right? Is it included? So they're including B. 1 is included in that interval. Let me just make sure I don't set you, because F is not differentiable. So there you go. So they just said the first one. So this is the one it doesn't apply to. And this is why. Because at x equals 1, it's not differentiable. So 0 to 2, it does not apply. Okay, 32. F at x equals x minus 1 to the 2/3. We did that one already. 32. From problem 31, use the interval on which it does apply, which is 1 through 9, to find the C values where the MVT is when the derivative is equal to A rock. So let's first of all do the derivative of this, which is 2/3 x minus 1, and then subtract 1 to the exponent. There's no hook. And then the A rock, the interval is 9 to 1. So we plug in 9. 9 take away 1. 9 take away 1 is 8. The cube root of 8 is 2, and 2 squared is 4. Plug in 1, and 1 take away 1 is 0. So I plug in and I get the answer 1/2. So I'm going to take the derivative equal to 1/2. And I'm going to solve it. So I'm going to multiply both sides. I'm going to do the reciprocal, because I think that's going to be helpful. Then multiply by 2. Divide by 3. Cube both sides. And then add 1. 9 over 9 is 1. So I get 73 over 9. Wait a second. Cube 3 and it's 27, right? So this is really 27 over 27. What is that? 91 over 27. So at that number, A rock equals I rock. That's good work. All right, 33. Can you do some graphing adjustments? Here we go. So I'm going to take the points that I see. This means it reflects over the y-axis, and then you add 1 to the y-coordinate. So if I'm going to reflect over the y-axis, I'm first looking at -2, -2. So if I reflect it, it's +2, +2, but it's up 1. I'm now looking at 0, 2. I can't reflect it, but I can go up 1. So now it's at 3, and then I connect these together. And then on the other side, reflect the point of inflection, which is at 1/2 and 1. So it'll be at 1/2 and 1 and go up 1. And if it reflects, the concavity will change a little bit. And then reflect the intercept. It goes to the left and then up 1. And then, well, that's it. Everything gets reflected up 1. Then it's going to look like that. So there's 33. Keep thinking here with me. All right, so this is affecting the x. So when the absolute value is on the inside, you only graph the right side. And then divide every x coordinate by 2. So if I take this and I divide it by 2, and divide this by 2, so I'm dividing the x's by 2, and then I reflect this picture on the other side. And that's what it looks like. 35. So this just affects the y-coordinate. It's a reflection, and then half the y. So what's below is above, and above is below. So -2 and -2 reflect, and then half. 0, 2 reflect, down, and then half, and then there's your line. The point of inflection is at 1/2 and 1, reflect, and then half. Can't reflect, half, nothing, so it stays right there. And then there, that's what it looks like. All right, last one, and then we're done. 36. The absolute value bars on the outside. This affects everything's going to shift to the left and reflect. And this one's going to reflect bottom, top, and top, bottom. So shift to the left. So that's now -4, and then reflect up. So we're at -4 and reflected up. Then I take 0, 2, shift it to the left, and that's going to be reflected. And there you go. Take the point of inflection, half and 1, reflect, so shift to the left 2, and reflect. Oh, wait a second. So shift to the left 2, and everything below goes above. I totally did bad work here. So you shift to the left 2, and anything below goes above. So this is going to be above. This point's going to be above. And then there you go. All right, we're moving on. Mr. G Math, I'm really proud of you that you did your work to the end. Till next time.